Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight, we're venturing far, farther than even the most distant planets you might remember from schoolroom posters. We're heading to a region of our solar system where the sun looks more like a star in the sky than the great glowing orb we feel on our faces. There, drifting slowly on a cold, lonely path, is something very small and very old. It's called Ammonite. But this isn't the fossil you might find curled in ancient rock. This Ammonite is made of ice and silence, and it may hold the memory of how our solar system began. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into Ammonite's story together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the tale. Out past Neptune, beyond even Pluto's long and lonely orbit, there is a kind of twilight zone. It isn't empty, not really, but it's quiet. So quiet, in fact, that for decades we barely noticed what lived out there. It's a region where time seems to stretch, where orbits last longer than the history of civilizations, where objects move slowly, not because they're sluggish, but because space itself becomes wider, emptier, and more indifferent to haste. It was in this stillness, in this cold ocean of light and shadow, that something began to tug at the edges of our attention. A faint point of light, barely shifting against the backdrop of stars. It didn't move quickly, it didn't shine brightly, but it moved. And that movement, over years of patient observation, was the first hint that we'd found something new, something ancient, something different, that something was eventually named Ammonite. Now, the name might bring to mind those beautiful spiral fossils, shells that curled into themselves like a nautilus caught in stone, and that's no accident. The scientists who found it chose the name because they saw something poetic in the shape of its orbit, and something even more poetic in the fact that it had remained unchanged for billions of years. Just like the fossils we find pressed into rock from Earth's distant past, Ammonite is a kind of time capsule, not made of calcium and sediment but of water ice, silence and memory. It was discovered not all at once but through layers of data, like peeling back a curtain made of time. The first observations came in 2023, with confirmation arriving in 2024. Scientists used telescopes perched high on dormant volcanoes, the Subaru telescope and the Canada-France-Hawaii telescope, both located on Mauna Kea, a mountain whose summit reaches above the clouds. These instruments, far from city lights and cradled by the thin, clear air of the upper atmosphere, have eyes sharper than anything we've built before. They watch the sky patiently, taking snapshots not just of stars but of the subtle changes between them. The camera used, called the Hyper Supreme Cam, is extraordinary. It contains 900 million pixels and can capture immense swaths of sky at once. But more impressive than its power is its patience. It wasn't just one picture that revealed Ammonite, but a sequence taken over months and years, like watching a single grain of sand shift slightly on a beach and realizing it's not sand at all, but a world. And that's what makes Ammonite so intriguing. It is a world, not a planet perhaps, not in the way we think of planets with clouds and moons and swirling storms, but a solid, round body, perhaps 220 to 380 kilometres wide. To compare, that's bigger than some moons in our solar system. It's certainly more massive than many asteroids. But what makes Ammonite special isn't just its size or its distance. It's the stillness it has preserved, the unchanged loop it has traced around the sun for longer than the Earth has had continents. It has orbited quietly, far from the inner chaos of the solar system, unbothered, untouched, and undisturbed. When you look at Ammonite's path, it's like looking at a piece of ancient calligraphy written in the margins of the solar system. A gentle curve, stretched long and thin, wrapping the sun at a great distance. At its closest point, it's 66 astronomical units away from the sun. That's 66 times the distance from Earth to the sun, and at its farthest it drifts 252 astronomical units from the centre of our solar system. Out there, sunlight is a suggestion more than a source of warmth. The photons that arrive take hours to travel that far. Ammonite, in turn, reflects only the faintest light back, so faint that for most of human history it was invisible, until now. And perhaps that's the most romantic part of this entire discovery. Not the technical brilliance, though, that is stunning. Not the long orbital calculations or the patient simulations, but the simple fact that something so old, so cold, and so quiet could finally be seen, finally be named. After all this time drifting on the edge of knowing, Ammonite was pulled gently into our awareness, not by accident, not by luck, but by a kind of soft persistence, a willingness to look and to listen. Because sometimes the universe speaks not in explosions or bright lights. Sometimes it speaks in slow spirals and cold orbits, in motion so subtle it takes years to see, in patience so deep it stretches across epochs, and in that silence, if we're quiet enough, then we might just hear something, like the soft breath of a fossil in the dark. High above the clouds, where the air is thin and the world feels both closer to the stars and farther from the worries of the ground below, sits a place made for watching. Mauna Kea, an ancient dormant volcano on the island of Hawaii, rises more than 13,000 feet above sea level. But when measured from its base on the ocean floor, it's even taller than Mount Everest. It is there, on this quiet, towering perch above the world, that scientists built a kind of listening post. Not for sound, but for light. Light so faint it barely registers, and so old it may have begun its journey when Earth's first multicellular creatures were still dreams of the deep. On that mountain, under a sky that blinks less than anywhere else on Earth, a camera was pointed outward. This wasn't just any camera. It was the Hyper Supreme Cam, a device with 900 million pixels stitched together to create an image of staggering clarity and depth. But it wasn't just clarity the scientists were after. It was time. The camera doesn't catch fireworks or flashes. It captures slow changes. The tiniest movement of a point of light over nights, then weeks, then years. Think of it like this. Imagine taking a photograph of a quiet field, then coming back a few days later to take another. If something shifted, a stone, a flower, a shadow, you might notice, but only if you were very, very careful. And in the case of Ammonite, it was like watching that field not for days or weeks, but for years, and noticing that one speck of starlight had nudged ever so slightly to the left. That's how Ammonite revealed itself, not with a roar, but with a whisper. Not in a blaze of glory, but through a long, patient pattern of movement. Over time, its slow arc became apparent. It wasn't a background star. It wasn't a camera glitch. It was something real. Something that was moving against the still tapestry of distant constellations. And that tiny motion, spread out over hundreds of days, told us it was part of our solar system. But a part we had never seen before. The discovery was part of a broader effort known as the Fossil Project, a lovely acronym for Formation of the Outer Solar System, an icy legacy. Fittingly poetic, considering what they found. The project brought together scientists from Japan, Taiwan, Canada, Korea and China, united not by a single observatory, but by a shared desire to understand the distant frontier of our cosmic neighbourhood. It was global cooperation in the most literal sense. nations coming together to study something so far away that even the sunlight reaching it had grown tired from the journey. The story of how they found Ammonite isn't just one of technology. It's a story of focus, collaboration, and the kind of intellectual quiet that takes years to bear fruit. The scientists working on this project didn't set out knowing they would find something like Ammonite. They were simply watching, cataloguing, measuring, and hoping. And when the data began to suggest something strange, something that didn't fit with the known patterns, they didn't ignore it. They leaned in. They looked closer. They let curiosity pull them forward. The process involved more than just spotting a dot in the sky. It meant confirming that dots motion across multiple nights using more than one telescope. Once something like Ammonite is spotted, astronomers must rule out other possibilities. It could be a comet, an asteroid, or a background object playing tricks with light. To confirm it's real, they compare images taken months or even years apart, looking for consistency, for that same subtle drift across the sky. If the object returns in the same arc and speed, then it isn't a fluke, it's a discovery. And that's what happened here. Bit by bit, image by image, the story of Ammonite emerged. It was given the temporary designation 2021 XA255, though no one will remember it by that name. Ammonite is far more fitting, ancient, coiled, and quietly profound. The challenge in discovering something like this lies in its remoteness. Ammonite is incredibly far away, and its reflectivity, its albedo, is low. That means it doesn't bounce much sunlight back to us. It's like a piece of old charcoal drifting in the dark. And yet, despite this, the sensitive instruments atop Mauna Kea caught it. More than caught it, they saw it moving. There's something beautiful in that, isn't there? That you can point a camera at a tiny portion of sky and wait, not for seconds or minutes, but for years, and eventually something long forgotten will stir. That by being still, by being watchful, we find the things that refuse to announce themselves. In many ways, the tools we build for astronomy are less about invention and more about humility. They remind us that the universe doesn't rush for us. It doesn't shine brighter to grab our attention. It simply waits. And when we learn to listen, really listen, to stare at a quiet place in the sky for as long as it takes, then the universe begins to tell us things. Not loudly, not all at once, but slowly, softly, as if whispering in a language made of time. So there on Mauna Kea, with instruments made from glass, silicon and mathematics, a group of humans caught the echo of something ancient. Not with shouts or songs, but with stillness. And that stillness, it turns out, was the only way to hear Ammonite. Because sometimes the most important discoveries are not loud. They're not fiery or explosive. They are gentle motions in the dark, specks of light that move just enough to say, I'm here. And now that we've seen it, now that we know it exists, Ammonite joins the small family of sednoids, those rare wanderers on the outskirts of our understanding. But before we talk about the family it belongs to, and how it challenges one of astronomy's boldest recent theories, let's take a moment to simply appreciate what it took to see it at all. It took patience. It took trust in our tools, in each other, and in the idea that the universe always has more to say. We just have to be quiet enough to hear it. When a new object is discovered in space, especially one as quiet and ancient as Ammonite, there's a moment of human hesitation. You've spotted something real. It has mass, movement, memory. It's not just a speck of data anymore. It's a character in the story of the cosmos. And now, it needs a name. But what do you call a world that has never been seen? A thing so distant that even its light takes more than half a day to arrive. You can't name it in a hurry. The name must echo across time, just as the object itself has. And so, the discoverers chose Ammonite. The name, like the object, carries weight. Ammonites were once sea creatures, spiral-shelled and soft-bodied, cousins of today's squid and octopus. They lived in Earth's oceans long before the first birds flew, long before the continents found their modern shapes. Their shells curled in tight spirals, and after their extinction, those spirals turned to stone. Over millions of years, they became fossils, symbols of deep time, of lost ecosystems, of life's long memory. To name a trans-Neptunian object after such a creature is more than poetic. It's a gesture of kinship. One fossil, ancient and turned to stone, found in mountains and quarries. Another fossil, icy and silent, found drifting beyond the known solar system. Both preserved, both patient, both telling stories from a time we'll never touch, but can still learn from. And if you tilt your head a little, if you imagine that long elliptical orbit as a spiral frozen in space, Ammonite's path around the sun even resembles that curling fossil shell. Not a perfect circle, but an extended loop, an echo of something organic, imprinted on the structure of space. Its physical size, estimated between 220 and 380 kilometers wide, sits in a curious place on the scale of celestial bodies. It's not large enough to be a planet. It may not even be round enough to be considered a dwarf planet by current standards, but it's certainly more than a rock. For comparison, it's larger than the asteroid Pallas, and about the same size as Saturn's moon Mimas, the one with a crater so large it looks like the Death Star from Star Wars. But unlike moons and asteroids that reside closer to home, Ammonite has been left almost entirely alone. No planetary gravity tugs at it regularly. No dense region of the solar system disrupts its motion. It lives in a space of rarefied quiet, a place where even the sun has trouble making its presence known. And perhaps that's why its surface, though never seen directly, is expected to be something extraordinary, frozen, ancient, unchanged. In the inner solar system, everything is restless. Planets churn with storms, atmospheres shift, surfaces erode, and volcanoes reshape the land. But out, beyond Neptune, things are different. There is no wind to blow across a dusty plain. There is no weather, no seasons, no tectonic drift. If something impacts Ammonite's surface, the scar may last for eternity. If sunlight ever slightly melts a surface patch, it likely freezes again, permanently etched into the frost. That means this object isn't just ancient in orbit, it's ancient in appearance. Every pockmark, every bump, every shadowed crater is potentially billions of years old. It is not just a visitor from deep time, it is a survivor of it. When scientists refer to it as a cosmic fossil, they're not being metaphorical. Ammonite truly preserves conditions from the solar system's earliest epochs, chemical fingerprints, orbital fingerprints, and maybe even structural ones. It holds memory, not in the way we hold it, not in thoughts or language, but in form, in temperature, in the way its body has remained still when everything else kept changing. Even its isolation is meaningful. Most objects in the solar system are part of crowded neighbourhoods. Asteroids jostle for space in the belt between Mars and Jupiter. Moons circle planets in nested loops. Kuiper Belt objects often feel the tug of Neptune, but Ammonite is detached, not just from the planets, but from the gravitational choreography of most nearby bodies. This detachment is part of what makes it so interesting, because it didn't just end up where it is by accident. Something, or many somethings, placed it there. Whether that's the ghostly hand of a passing star, the echo of a long-lost planet, or the memory of the sun's chaotic youth, we don't yet know, but the clues are in its stillness. To name an object like this is to admit that even in the face of all our technology, all our equations and computer models, there is still something ancient and unknowable hovering just beyond the maps, and we've found it. More than found it, we've welcomed it into our story. Because even though it took a telescope the size of a school bus and a camera sharper than any human eye to see it once it was named, Ammonite became something else. Not just a frozen body, not just a set of coordinates, but a character, a whisper from the edge of the firelight, a curve drawn in the dark, and now, in the years to come, as more telescopes turn their gaze toward it, as more data is collected and orbits refined, that name will remain, just as the fossil ammonites remain, carved into cliffs, encased in ancient seabeds, spiraled in silence, symbols of life that once was and still echoes. So next time you pick up a fossil, one of those beautiful coils from deep beneath the soil, imagine another one, far out in space, spinning slowly through a sea of stars. It's not made of stone, but it holds memory just the same, and it is still moving, still circling, still waiting to be understood. Imagine you are drifting in the deepest part of winter. Not the kind of cold that bites at your fingers, but something more distant. A quiet, endless frost where warmth is a memory and movement feels optional. This is the kind of cold where Ammonite lives, and in this cold, it moves. Not quickly, not with urgency, but with grace. A kind of slow, deliberate loop carved in the fabric of space. Its path around the sun is not circular, not quite tidy, and not anywhere near the planets we know. It is stretched, eccentric, and most of all, distant. Let's begin close to home. Earth orbits the Sun at what astronomers call 1 astronomical unit, or AU. It's a simple concept. The average distance between Earth and the Sun, about 150 million kilometres. It's the ruler we use to measure the rest of the solar system. Venus sits at around 0.7 astronomical units, Mars just over 1.5. Jupiter, the gas giant with its thick swirling clouds, lounges at around 5 astronomical units, and then there's Pluto, still trailing its icy tail at about 40 astronomical units, orbiting in the chill beyond Neptune. But Ammonite plays by different rules. At its closest, it's 66 astronomical units from the Sun. That's 66 times farther than we are. So far that sunlight there is dimmer than twilight, and it takes over 9 hours for a photon to arrive. If the Sun is a campfire, Ammonite doesn't sit around it like the planets do. It doesn't roast marshmallows or bask in the glow. It's the leaf lying on the forest floor, far beyond the circle of light, fluttering gently when the flames crackle, still warmed, faintly, distantly, but never touched. And that's just its nearest point. At its farthest, Ammonite stretches out to 252 astronomical units. That's over 6 times farther than Pluto, a realm where light itself moves with hesitation, where temperatures hover near absolute zero and the background stars become your only consistent companions. There's no planet to pull on it, no moon to orbit, no gravitational conversations to join. It circles the Sun in a long ellipse, a frozen dance that takes thousands of years to complete. One loop, one return, over spans that dwarf all of recorded human history. But it's not just the distance that makes its orbit remarkable, it's the nature of it. Most orbits in the solar system, even the more eccentric ones, are shaped by their relationships. Neptune nudges Pluto, Jupiter commands the asteroid belt, Saturn keeps its moons in tight formation, but Ammonite's orbit is detached. It doesn't cross paths with any known planet. It doesn't dip into the neighbourhoods of Neptune or Uranus. It floats in a space that feels unanchored, like a melody played without a metronome. Astronomers call orbits like this detached. Detached from Neptune, specifically, the outermost planet with enough mass to seriously disturb smaller objects. And that word, detached, is more than technical. It's emotional. It conjures the image of a traveller who has long since said goodbye to the crowded warmth of planetary society and has chosen a quieter, more solitary path, not lost, not forgotten, just apart. This kind of orbit shouldn't exist easily. The Sun's gravity fades with distance, but it never entirely lets go, and yet Ammonite seems to hang in a region where neither the Sun nor the outer planets exert full control. It's a liminal space, between presence and absence, between influence and independence. And so its motion is slow. Not sluggish, not reluctant, but patient. It carries the poise of an old, quiet satellite, one that remembers the early symphony of the solar system and chooses to move according to a rhythm long faded. One trip around the sun might take it tens of thousands of years. That means it has only completed a few orbits since the planets first formed. While civilizations have risen and fallen on Earth, while species have come and gone, while oceans have shifted and continents have collided, Ammonite has been tracing the same path, unhurried, unchanged. And here's something gentle to hold on to. When we observe Ammonite from Earth, we're not just seeing it as it is, we're seeing it as it was 9 hours ago, the time it took for its reflected sunlight to reach us. We're always looking at a slightly younger Ammonite, just like we look at the moon and see it a little over a second in the past, just like we look at distant stars and see them centuries or millennia out of sync. This idea that everything we observe is a glimpse into what was, not what is, adds a layer of softness to its motion. It's as if the object itself is wrapped in memory, always arriving just a little late, as if giving us time to prepare. We might wonder what placed Ammonite in such a strange orbit. Why does it move the way it does? And why do so few others seem to join it? Those questions will come, but for now, it's enough to understand that this object is not ruled by Neptune's pull. It is not pulled into resonance like Pluto or scattered like a comet. It exists in a realm of subtlety. Its motion is governed not by close encounters, but by history, by inertia, by whatever slow ancient forces once passed through the solar system and left barely visible footprints. Ammonite's orbit is one of those footprints. It is long, it is quiet, and it is not quite free. It still circles the sun, still bound by the faint thread of gravity, but it is not part of the chorus anymore. It is a soloist, gliding on the outskirts of the great celestial stage. In this way, Ammonite reminds us of something easily forgotten in science. Not all that is unknown must be dramatic. Not every mystery roars. Some whisper. Some move gently, in ways that make us pause. And some, like this one, loop far out in the cold, reminding us that even at the edge of our maps, there are stories still unfolding, stories that circle slowly like leaves in far-off light. Ammonite is not entirely alone out there in the cold. There are others like it, though not many. The solar system is vast, and its outer regions are particularly empty by the standards of human imagination. But now and then something appears, another distant drifting light that doesn't follow the usual rules. These objects, rare and mysterious, are part of an extremely exclusive group. Astronomers call them sednoids. The name comes from Sedna, the first and most well-known member of this class. Discovered in 2003, Sedna stunned astronomers not because it was large, it's roughly 1,000 kilometres across, but because of where it was found. Its orbit, like Ammonite's, is detached. Its path doesn't bring it close to any of the major planets. It doesn't interact with Jupiter or Neptune. It simply moves, slowly and silently, through a space where almost nothing else is. Sedna's closest point to the Sun is about 76 astronomical units, and it stretches out beyond 900 astronomical units at its farthest. That's more than 30 times farther than Neptune. For context, if Earth's orbit is the width of a sidewalk, Sedna's loop would reach past the far end of a neighbourhood, far enough that streetlights grow thin and the stars feel closer than home. And just like Ammonite, Sedna takes thousands of years to make one trip around the Sun. The ancient Egyptians had not yet built the pyramids the last time it was near its closest approach. The next time it returns, countless generations from now, the world will have changed again. In the years that followed Sedna's discovery, astronomers found a few others with similarly peculiar orbits. 2012 VP113, nicknamed Biden, is one of them. Another is Leleakuhonua, whose name comes from Hawaiian mythology, and means the distant heavenly wandering one. Each of these objects has a path that doesn't quite fit with what we'd expect from standard solar system models. Their orbits are elongated, off-centre and unusually inclined. They don't dance to the rhythms of the planets we know. Instead, they seem to be following some other tune, one we can't fully hear. That's where Ammonite comes in. With its elongated orbit stretching from 66 to 252 astronomical units, it joins this strange family. But interestingly, it doesn't quite align with them. You see, when astronomers first discovered sednoids, they noticed something odd. Many of them seemed to be clustered. They pointed in roughly the same direction in space. Their closest approaches, their perihelia, were aligned in a way that didn't look random. Imagine drawing their orbits on a giant sheet of cosmic paper. You'd notice the shapes weren't scattered like confetti. Instead, they looked like petals on a flower, tilted but organised, as if shaped by a common hand. This clustering was strange. According to the laws of gravity, the outer solar system should be more chaotic. Random encounters with passing stars or the slow tug of galactic tides should scatter these objects over time. But the sednoids weren't scattered. They were oddly tidy. And that tidiness raised a question. What was keeping them organised? That question led to a hypothesis, one that captured the imagination of scientists and the public alike. Maybe, just maybe, there was something massive out there. Something we hadn't seen. Something large enough to shepherd these distant objects into neat patterns. A planet. A ninth planet. The Planet 9 hypothesis was born. Unlike Pluto, which was reclassified as a dwarf planet, this new potential planet was theorised to be large, maybe 6 to 10 times the mass of Earth. It would orbit far beyond Neptune, perhaps hundreds of astronomical units away, and would take tens of thousands of years to complete a single orbit. It wouldn't be visible with current telescopes unless we happened to be looking in exactly the right direction. But its gravitational influence, that might show up in the orbits of the sednoids. It might explain the clustering. It might explain why they weren't scattered, but shaped. For a while, Planet 9 seemed to make everything make sense. But then came Ammonite. When its orbit was plotted, it didn't fit the pattern. Its perihelion, the point where it comes closest to the Sun, wasn't aligned with the others. It wasn't pointing in the same direction. It wasn't tilted the same way. It wasn't cooperating. And suddenly, the neat story began to unravel. Because if all the sednoids were shaped by Planet 9, then they should all point the same way. But if one doesn't, and especially if more like Ammonite are found that also don't, then maybe Planet 9 isn't the answer. Or maybe the story is more complicated. Perhaps multiple forces are at play. Maybe the clustering was a coincidence. Maybe something else, something older or stranger, shaped these orbits long ago, and the pattern we saw was just the part of the iceberg above the waterline. That doesn't mean Planet 9 isn't real. It just means the picture is fuzzier now, less certain. And in science, that's not a bad thing. It means we're still learning. It means the universe is still surprising us. Ammonite is the first sednoid to challenge the cluster, to whisper that maybe the others aren't as tightly linked as we thought. It complicates the theory, and in doing so, it deepens the mystery. It reminds us that every new discovery is not just an answer, it's also a question. And perhaps that's the most sednoid thing about Ammonite. It didn't just join a family, it shook it gently awake. There is a certain kind of silence in astronomy, one that isn't about the absence of sound, but the absence of certainty. A stillness not born from peace, but from waiting. Planet 9 lives in that silence. Not because we've seen it. We haven't. No telescope has captured a blurry image. No satellite has logged a shadow passing across a field of stars. But the idea of it exists, lingering just beyond the edge of vision, stitched into equations, whispered by orbits, suggested by patterns that seem too clean to be chance. The Planet 9 hypothesis emerged not from wild speculation, but from mathematical necessity, or at least the suggestion of it. When astronomers noticed that a group of distant objects in the outer solar system, including Sedna and 2012 VP113, appeared to be clustered in space, it raised a question. What was keeping them that way? Gravity, after all, is the great organizer of the cosmos. It's the invisible hand that turns clouds of dust into stars, stars into galaxies, and galaxies into slow, spiralling ballets. So when distant, icy objects in the solar system all seem to point in similar directions, when their elongated orbits appeared to be aligned in a way that resisted randomness, astronomers did what they always do. They asked what unseen force might be pulling the strings. The answer, or at least the most elegant one, was this. There may be a planet, larger than Earth, orbiting the Sun far beyond Neptune. A true planet. Not a dwarf, not a scattered remnant, but a full-fledged member of the solar family, hiding in the dark. It would be massive enough to exert gravitational influence over nearby objects, even those hundreds of astronomical units away. It would move slowly, so slowly, that even decades of sky surveys might miss it if it wasn't in the right part of the sky at the right time. It's important to say this. The idea is still a hypothesis, a possibility, a beautiful, plausible maybe. And it has captured the imagination of scientists and the public alike, because it feels like something out of an old explorer's map. Here be dragons, the corners used to say. And now, in the cold reaches past Neptune, we wonder if something large is indeed lurking just out of sight. But Ammonite, quiet and unassuming as it is, may be the soft wind that stirs the edge of that old map. Its orbit, while distant and detached like those of the clustered sednoids, doesn't point in the same direction. It breaks the pattern. It refuses the choreography. It arrives on stage and quietly chooses not to follow the other dancers. And that causes a kind of gentle tremble in the Planet 9 hypothesis. Because if Planet 9 is out there, guiding these icy bodies into aligned orbits with its invisible hand, then why doesn't Ammonite align? Why doesn't it obey? One possibility, of course, is that Ammonite is an outlier, a single exception in a population that otherwise follows the rules. Statistical blips happen, but science is careful, especially when the numbers are small, and the numbers here are very small. Only a handful of sednoids are known. With such a tiny sample size, even one object refusing to fit the mould forces us to re-examine the whole picture. Another possibility is that there is no Planet 9 at all, that the clustering we observed was a coincidence, or the result of observational bias. We tend to look in certain parts of the sky more often than others. Our telescopes have limits, our data sets are lopsided. If we imagine the solar system as a canvas, we've only painted in parts of it. It's possible that once we fill in more of the picture, the pattern will dissolve and the sednoids will scatter like leaves in wind. But there's also a third possibility, one that keeps both the mystery and the poetry alive. Perhaps the outer solar system is shaped by more than one influence. Maybe Planet 9 exists, but it's not the only sculptor. Perhaps long ago, when the sun was still young, it shared its birth cluster with many other stars. And perhaps, in that crowded nursery, one or more of those sibling stars drifted close enough to tug at the outer disk of planetesimals, sending some into strange orbits like Ammonites. A passing ghost of a star, a slow ripple in the gravitational pond, a memory written in motion. Or maybe, once upon a time, the solar system had more planets. Planets that no longer exist, lost to ejection, collision, or slow decay. A rogue planet that wandered too far and was flung into the dark. A giant body that passed too close and was torn apart. These ghosts, though gone, could have left their fingerprints behind, in paths like Ammonites, in scars invisible to the eye but preserved in gravity's quiet accounting. Whatever the explanation, Ammonite complicates things, not rudely, not disruptively, but softly, like a single out-of-place star in an otherwise well-ordered constellation. It invites reconsideration. It asks us to look again, to expand our search, to reframe the narrative. This is the nature of science at the edge. We build theories not as final answers, but as scaffolding, temporary frameworks to help us see more clearly, and then sometimes something shifts. One new discovery, one new orbit, one distant object that doesn't do what we expected, and suddenly the scaffolding must be adjusted, rebalanced, rebuilt. Ammonite doesn't destroy the idea of Planet 9. It simply whispers that the truth may be broader, messier, and more beautiful than we thought. That the outer solar system isn't a quiet void, but a place of complexity and history. That every orbit is a story, and some stories don't fit the outline. In that sense, Ammonite is not just a fossil, it's a revision. A soft red pen moving through our cosmic manuscript, suggesting that perhaps this paragraph needs a little more space. And maybe that's the lesson it carries, that the universe is not obligated to confirm our theories. That wonder often begins where certainty ends, that the next great truth may arrive not with thunder or headlines, but with a quiet orbit curving through the dark, asking us to listen more closely. In a library of stars, Ammonite is a forgotten page, one that was never erased, never rewritten, only quietly folded and left in the binding. Its orbit, arcing silently beyond the planetary stage, is not a recent note scribbled in the margins. It is the ink itself, faded but legible, curved like the script of an author long gone. And what it tells us, if we know how to read it, is that memory lives not only in fossils or ice or rock, but in the very movement of things. Orbits, after all, are a kind of language, not written with letters or sound, but with gravity. Each one tells a story, not only of where a body is, but where it has been and what has touched it. The shape of an orbit, its eccentricity, its tilt, its resonance with others, these are echoes, soft fingerprints left by past encounters, long past neighbours, or even absences that once shaped the shapeable. Ammonite's orbit, like that of Sedna and its kin, is especially haunting because it appears stable, not merely quiet, not just slow, but unchanging. And that stability, stretched across billions of years, is what makes it so compelling. Our solar system is not a place of rest. The inner planets shift ever so slightly over time. The asteroid belt churns with subtle chaos. Comets come and go. Even the outer planets tug on each other in imperceptible rhythms. Over millions of years, small changes accumulate, reshaping the clockwork ever so slightly. It is not disorder, it is evolution. But Ammonite, it seems, has not changed, not meaningfully. Its path remains as it was, arcing from the outer Kuiper belt into a region few bodies dare to tread. It hasn't been flung inward. It hasn't been perturbed by Neptune's slow magnetism. It hasn't spiralled away. Its eccentric loop is not only wide, it is faithful, a nearly perfect record of a time before order settled in. To understand why this matters, we need to look not just at its current position, but at the simulation of its path backward through time. Astronomers use computational models, mathematical time machines, to wind the orbits of solar system bodies back through millions, even billions of years. With each rewind, with each data point recalculated, a picture emerges of where that object might have been, and how its orbit has changed. And in Ammonite's case, the result is astonishing. For over 4.5 billion years, since the earliest days of the Sun's ignition, its orbit has remained largely undisturbed. A stable, detached ellipse, barely touched by the shifting gravities of planetary migration or chaotic jostling. Like an ancient signature that hasn't been smudged. This is why astronomers call it a fossil orbit. Not just because it is old, but because it preserves the conditions of a younger, more volatile solar system. A kind of spatial relic, pure, undistorted and precious in its preservation. Imagine this. While Earth was being pummeled by asteroids, while its oceans were forming, while life was tentatively emerging in the warmth of deep-sea vents, Ammonite was already circling, at the edge, in the cold, quietly tracing its arc around a star that had only just found its light. Its loop is so long, so distant, that the number of times it has orbited the sun could be counted not in millions, but in handfuls. 5, maybe 6, perhaps 7 full revolutions since it formed, each orbit a chapter in a very slow book, each pass taking thousands of Earth years, so long that entire species have come and gone in the span of a single loop. The idea that a world could remain so unchanged for so long is humbling. In a cosmos where everything evolves, shifts, collides and reforms, Ammonite is a stillness that defies the trend, a kind of protest against chaos, or perhaps more gently, a memory of a time when chaos had not yet settled into rhythm. There's something comforting about this. We often think of the cosmos as unpredictable, dangerous, full of sudden bursts and violent ends, and it can be. But it can also be this, an object, tiny and cold, following a path so steady and so old that it has become a thread sewn into the outer lining of the solar system's coat. Even its orbit, mathematically defined and plotted, has a softness to it when seen at the right scale. No jagged turns, no rapid spirals, just a long, pale ellipse, a quiet oval stretched across light years of space, like a painter's brushstroke left to dry. If orbits are memory, then Ammonite remembers a time when the planets were still forming, when Jupiter hadn't yet claimed its moons, when Saturn's rings were whispers, and Earth's continents were still possibilities, not facts. It remembers a time before Neptune had reached its current home, before the Kuiper Belt was a belt at all. And it remembers all of this not through any conscious awareness, but by simply continuing, by not being interrupted. Perhaps this is the true power of stability, not as stillness, but as silent witness. Ammonite is not a storyteller, not in the way we are, but it carries the story nonetheless. It is a vessel for memory, a physical arc that has remained faithful to its origin. And every time we chart its path, we are reading a sentence from the first chapter of our cosmic novel. So the next time you look up into the night sky and wonder what's out there, remember that some of what's out there is not just distant in space, but in time. That there are objects whose journeys began when nothing on Earth had a name, and who have kept circling ever since. Ammonite is one of them, a cold signature on the parchment of space, a curve etched in the dark, a traveller that never changed its course. And as we continue our own spinning journey around the sun, it's comforting to know that somewhere out there, in the great quiet distances, a small, ancient world continues to loop, steadily, silently, through the memory of everything that came before. Before the sun was the quiet centre of our solar system, before Earth had continents or moons, before Ammonite had a name or an orbit, the sun was just one star among many. It was young then, newly ignited, still wrapped in the loose cradle of a star-forming region, surrounded by the dust and gas that would one day become planets. And in that nursery, it was not alone. Stars are rarely born solo. Like siblings, they come in clusters, hundreds, sometimes thousands, emerging together from the same sprawling cloud. In their infancy, they orbit a common centre of gravity, drifting slowly apart over millions of years. And during that time, when the sun was still young, still warming up, something extraordinary may have happened. A nearby star may have passed close, not close in the way we think of cars on a road or birds brushing past each other in flight. Not even close in the way comets pass near planets. In space, close can still mean trillions of kilometres. But for gravitational influence, that's near enough. If a star passes within a few hundred astronomical units, say inside 1000 AU, it can tug gently on the objects in a young solar system's outer disk, And those tugs, even if soft, can shift orbits permanently. Imagine the solar system then, not as the structured dance we know now, but as a hazy disk of ice and dust stretching far beyond the planets that hadn't yet formed. A cloudy halo of building blocks, frozen and drifting, waiting for something to settle them. Now picture another star, moving slowly through the dark, passing through the outer edge of that disk. Its own planets may have been forming, its own system still a secret. It doesn't collide, it doesn't burn, it doesn't even slow down. But it nudges, just enough. The gravity of that stranger, quiet, indifferent, but real, would have disrupted the balance at the solar system's edge, not with violence, but with suggestion. Orbits that might have been circular become ovals, paths that once lay flat tilt upward. Some material is pulled inward, some is flung outward, and some, like the body that would one day be called Ammonite, finds a new path entirely, not inward, not ejected, but set adrift in a stable, strange ellipse, far from the chaos of planets, yet still part of the sun's realm. It's not an uncommon theory. In fact, it's becoming increasingly accepted that close stellar flybys likely played a role in shaping the outer architecture of many planetary systems, and for our own solar system, it may explain the presence of sednoids, those rare bodies with distant detached orbits that don't conform to the usual gravitational models. To imagine this is to reframe the solar system not as an isolated island, but as a once crowded ocean. A place where stars sailed past one another in slow motion, a time when neighbours drifted near, unknowingly writing each other's future with invisible hands. The evidence is subtle, but compelling. Objects like Ammonite have orbits that suggest they were disturbed early, very early, not by the current planets, whose pull doesn't reach far enough, not by comets, which are too small, but perhaps by something much larger, much older, and now long gone. The image often used is that of a snow globe. Picture the early solar system as a globe filled with icy particles, gently settled into a disk. Then imagine shaking it. Not wildly, but just enough for everything to swirl. That's what a passing star might have done. A brief encounter, a momentary tilt, a stirring of orbits that took mere centuries but left patterns lasting billions of years. Ammonite then is one of those swirling pieces of ice, shaken loose, but not flung away, not lost to interstellar space, not scattered beyond recovery, just shifted, sent on a loop that no longer aligns with the rest of the system, a body that remembers the moment when the snow globe was stirred, and still carries that motion like a whisper in its path. Of course, the star that did the stirring is long gone. It may be halfway across the galaxy now. We don't know which one it was. Maybe it was a sibling of the sun, born from the same cloud, sharing the same chemical fingerprints. Maybe it was a stranger, just passing through. We may never know. The sky is too full of stars and time has erased their tracks. But we do know that close stellar encounters happen. And we know that our solar system bears the fingerprints of at least one. That idea, that a star once passed close enough to change the shape of our system, and then continued on, never to be seen again, is both humbling and poetic. It reframes everything we know as part of something larger. A chapter in a longer book. A conversation in a crowded room that has since gone quiet. And in that silence, in the orbits of objects like Ammonite, we find the echoes. We find orbits that don't quite belong. Shapes that speak of a moment we can't witness, but can still trace. Patterns that suggest, gently, that the solar system we see today was never inevitable. It was sculpted, not just from within, but from without. Not just by gravity, but by memory. So when we think of Ammonite's long, lonely path, we might also think of that silent star. The one that passed by without announcement. The one that reached out, touched the outer edge of a forming system and left. No fanfare, no fireworks. just a soft permanent ripple in the orbits of ice and rock. And somehow that ripple is still moving, still circling, still visible if you know how to look. Not everything leaves a crater, not every influence shouts. Some just brush past in the dark and reshape the future, quietly and forever. There's a strange kind of melancholy in the idea that something might have existed, shaped the world we know, and then disappeared without a trace. Not everything leaves ruins, not everything leaves fossils. Some things leave only silence, and the shape of that silence is what scientists spend lifetimes trying to interpret. Among the many theories to explain the strange orbits of objects like Ammonite, one of the most haunting is this. Maybe a planet once lived in the outer solar system. A real planet, massive and cold, wandering far from the heat of the sun. It might have formed in the same burst of creation that gave us Jupiter, Saturn and Neptune. It might have orbited calmly, steadily, circling in the frozen reaches far beyond Pluto. And then, sometime in that long and hidden past, it vanished. Not in a puff of smoke, not in a dramatic explosion. It simply left. Or more precisely, it was flung. In the early solar system, planets did not yet know their final paths. The giants, Jupiter and Saturn especially, were restless. As they migrated, drawn by the shifting tides of gas and debris, their gravitational pulls created chaos. Orbits overlapped, resonances clashed, smaller bodies were scattered like leaves in a sudden wind. And if there had been another large planet, an ice giant perhaps, or a rogue protoplanet, it might have found itself in the crosshairs of this gravitational reshuffling. It could have been nudged into a collision with another planet, or more likely, pulled into a trajectory that accelerated it beyond the reach of the sun's gravity. One too many encounters with Jupiter or Saturn, and the object could be ejected entirely, flung into the black, joining the countless rogue planets that now wander the galaxy between stars. But before it left, if it existed at all, it might have left behind traces, not pieces of itself, not debris or moons or craters, but gravitational signatures, ghosts in motion. Imagine this. As that long-lost planet drifted through the outskirts of the young solar system, it passed near objects like Ammonite. Not close enough to destroy them, not close enough to pull them into orbits of its own, but close enough to nudge, just slightly. Enough to stretch an orbit, to tilt a path, to dislodge a body from the crowded Kuiper belt and set it on a strange solitary loop. Those nudges would have been gentle, gravitational whispers rather than shouts. But in space, subtlety is destiny. A small change today becomes a vast difference over time, and Ammonite's odd elongated orbit, its detachment from Neptune's influence, its stubborn refusal to follow the patterns of its sednoid cousins, might be the residue of such an encounter. This is not just poetic thinking. Simulations suggest it's possible, perhaps even likely, that our solar system once contained more planets than it does now. Some may have merged, some may have been consumed by the sun, and some perhaps were exiled by the very system that formed them. We call them ghost planets, but they are not supernatural. They're only lost, hypothetical, suggested by patterns that don't quite fit. We haven't seen them. We may never find them. But like archaeologists finding gaps in a mosaic, we infer their shape by the space they left behind. In this way, absence becomes a kind of presence. We often think of discovery as a process of addition, finding new things, adding them to our maps, confirming their existence. But in astronomy, and especially in planetary science, we also discover by subtraction. We notice what doesn't, align what's missing, what should be there, but isn't. And then we ask why. Ammonite in its orbit suggests something happened. Its path is too stable to be random, too isolated to be explained by known forces alone. It is as if it remembers something that no longer exists. A gravitational hand that brushed past once and then disappeared. And yet, that one moment, perhaps brief, perhaps unrecorded, shaped everything Ammonite would become. This gives us a strange kind of emotional language for orbits. We can begin to see them not just as mathematical curves, but as expressions of history, a memory written not in stone, but in motion. And in that motion, we glimpse the shape of a missing presence. It's a little like seeing the impression of a body on an old mattress. No one is lying there now, but you can tell that someone once was. The shape lingers. The weight is gone, but the story remains. If there was a ghost planet, it may never return. It may be floating between stars now, silent and unlit, its surface frozen, its orbit unanchored. Or perhaps it was pulled into another system, another sun where it began again. Or maybe, just maybe, it circles the sun still, too distant to see, too faint to notice, but real nonetheless. Whether it's real or not, the possibility humbles us. It reminds us that the solar system we see today is not the whole story. It's the current chapter in a much longer book. An Ammonite drifting far beyond the planets is one of the pages where the ink never quite dried. To hold a fossil in your hand is to imagine the creature it came from. To read a line of poetry is to hear the voice that once spoke it. And to trace Ammonite's orbit is to wonder what passed near, long ago, and left without saying goodbye. So we call it a ghost, not because it haunts us, but because it touches us with something just beyond knowing. There's a kind of science that doesn't look through a telescope or gather samples from a rocky plain. It doesn't smell like dust or hum with electric motors. It doesn't use hammers, probes, or parachutes. Instead, it sits in the hum of processors and the soft whir of cooling fans. It waits in dark rooms and quiet servers, watching numbers move, calculating futures that never came to pass and pasts that may have never been. This is the science of simulation. When it comes to something as ancient, delicate, and far away as Ammonite, simulation becomes our telescope. We cannot send a spacecraft, at least not yet. We cannot scoop up its ice or drill into its crust. But we can rewind its orbit, gently, mathematically, using the laws of physics as our film projector. The idea is simple, though the execution is anything but. Start with what we know. Ammonite's current position, its orbit, its velocity, its distance from the sun. Input those numbers into a simulation, then add in the planets, Jupiter, Saturn, Uranus, Neptune, the great architects of the solar system's shape. Let the system evolve. Press rewind not in seconds or minutes, but in thousands, millions, even billions of years. Let gravity speak, and what emerges is not a single answer, but a chorus of possibilities. Some models suggest that Ammonite, along with other sednoids, may once have shared similar orbits, aligned more neatly, resonant, like dancers beginning a waltz, steps in time drawn together by some early choreography. But over time, whether because of passing stars, shifting planetary giants, or the fluttering chaos of small influences, they began to drift apart, like partners who lost the beat, not abruptly, but slowly, a gentle unravelling of resonance. This concept, orbital resonance, is one of the most beautiful in celestial mechanics. It describes the way objects can find rhythm with one another, even across vast distances. A resonance isn't a collision or a capture, it's a relationship of timing. For every 2 orbits of one body, the other might complete exactly 3. Over time, these ratios lock in, like dancers falling into step. Moons do this around Jupiter, Pluto and Neptune do this across their icy gulf. But for Ammonite and its kin, if such a resonance ever existed, it has since faded. Simulations show divergence, slow, patient, inevitable. Orbits that were once similar are now spread like ink across a page. Still readable, still from the same pen, but no longer tidy. Some loops have tilted, others have stretched. A few remain curiously aligned, but the overall pattern is loosening, And in that loosening, there's a story. Imagine a room filled with pendulums, dozens of them, swinging in synchrony. At first, the motion is mesmerising, a wave of harmony, but then a small push here, a slight draft there. One pendulum lags, another rushes forward. Slowly the pattern degrades. It doesn't collapse exactly. It softens. It becomes a memory of order, rather than order itself. This is what may have happened in the far reaches of the solar system. A dance that began with elegance, then unravelled, not into chaos, but into quiet individuality. Each sednoid now circling in its own rhythm. Still distant cousins, still related, but no longer aligned. For Ammonite, this divergence is especially pronounced. Its orbit doesn't fit the existing models neatly, and that makes it valuable. It's not the centre of the pattern, it's the edge. And in science, edges matter. They tell us where our theories bend, where they stretch, where they might break, and sometimes where new ones begin. Simulations are also helping us ask broader questions. What if there was once a whole population of sednoids? Dozens, maybe hundreds, most too small to see, some flung outward, others lost in the glare of the Milky Way. What if Ammonite is one of the survivors of a forgotten age, when the outer solar system was more crowded, more dynamic, more alive with movement? And what if we're only now beginning to rediscover that age? Each simulation adds another thread to the tapestry. It doesn't give us certainty, it gives us possibility, a constellation of maybes. And while that might frustrate those who crave answers, it also creates a space for imagination to meet mathematics. There's a reason ancient myths often describe the heavens as dancers, weavers, singers. Before we had equations, we had rhythm, and in the slow arcs of these distant bodies, rhythm remains, a rhythm distorted but not silenced. One simulation shows Ammonite sharing a rough orbital plane with Sedna, briefly, millions of years ago, before veering off. Another suggests a cluster of orbits aligned, then gently splayed by a single disruption, perhaps a migrating Neptune, perhaps a ghost planet passing through, perhaps a stellar whisper long since forgotten. In that view, Ammonite is like a lone violin playing a part of a symphony no longer performed. We don't hear the full composition anymore, but the notes it plays still carry echoes of the original music. And as we continue to run these simulations, refining our inputs, adjusting our models, widening our view, we begin to understand something fundamental. Not just about Ammonite, but about ourselves. We are not looking into space merely to catalogue rocks and ice. We are listening for rhythm, for stories, for movement, for meaning. Because orbits are not just paths, they are the fingerprints of history. An Ammonite's path, with its slow defiance and ancient curve, is a line drawn from a forgotten chapter. A dance interrupted, a resonance faded, a memory still in motion. In the cold reaches beyond Pluto, where the sun has long since faded to a pale memory, Ammonite turns slowly in the dark. It is not a dramatic place. No volcanoes, no wind, no flowing rivers of methane or lightning storms of hydrogen. There is no tectonic push or atmospheric swirl to shape its face, no internal heat to crack the crust or churn the surface. It is still. And because of that stillness, it remembers. Its body is small by planetary standards, perhaps only a few hundred kilometres across. But in that frozen frame, it holds something most ancient worlds no longer do: preservation. A kind of geologic silence. The surface of Ammonite has likely remained untouched for billions of years. No rain has fallen. No erosion has worn away the details. No seismic convulsions have erased the history beneath. It is, as far as we can tell, a world that has been quietly waiting since the solar system was young. That surface, unweathered, unchanged, is composed of ice and rock, But not just any ice, not the fleeting frost on your window or the sculpted snow of Earth's poles. This ice is old, cosmic, likely made of frozen water mixed with silicates, methane, ammonia, and organic compounds formed in the primordial cloud that birthed the sun. And those materials, arranged molecule by molecule, are the same ones that once swirled in the disk from which the planets were born. To study Ammonite is to study the leftovers of creation. Water ice may seem mundane to us, but it plays a central role in the formation of planetary systems. It allows small grains of dust to stick together, to coalesce into larger structures. It forms the scaffolding upon which planetesimals grow, and when preserved, as it is on Ammonite, it carries the isotopic fingerprints of its origin, where it formed, how it formed, and what nearby influences shaped its chemistry. The silicates within Ammonite tell a similar story. These rocky minerals, abundant in the early solar system, often come from high-temperature regions closer to the sun. So if Ammonite has them, it suggests either that they migrated outward in the turbulent disk of early dust and gas, or that the entire cloud was far more dynamic than we once thought. Each grain tells a tale of movement, of assembly, of temperature gradients and chemical reactions that once unfolded on a scale no eye could see. Then there are the organics. These aren't the building blocks of life necessarily, but they are cousins, long chains of carbon-based molecules formed through photochemistry and radiation. On Ammonite, they likely drifted in with the dust, or formed in place under the influence of the weak but persistent cosmic rays that bathe the outer solar system. Left untouched for billions of years, they sit now like sentences frozen mid-word, fragments of chemistry waiting to be read. What's remarkable about Ammonite is not only what it's made of, but what has not happened to it. Unlike planets with atmospheres, where weather sculpts the landscape, or moons with internal heating, where tidal stresses create fissures and plumes, Ammonite is a quiet world. Its lack of atmosphere means that meteoroid impacts are not cushioned. They strike directly, leaving scars. But those scars remain. Nothing erodes them. Nothing smooths them over. They stack, layering over one another, a record written not in years but in eons. In this way, Ammonite is a kind of crystalline archive, a library of ancient chemistry, never reshelved. Its surface chemistry is likely the same today as it was when trilobites first stirred in Earth's oceans, or even earlier when the Earth itself was a molten sphere. And yet, we haven't touched it. We haven't sent a probe. We haven't seen its face in detail. What we know comes from careful measurements, from reflected light, from subtle shifts in orbit and motion. But even that light, the faint photons bouncing off its icy surface and travelling for hours through space to reach our instruments, tells us something. It tells us that Ammonite is cold, that its ice has not melted, not even slightly, that its albedo, its reflectivity, fits with a surface coated in aged, sun-dulled frost, and it tells us that the surface has not been altered by geological change. No cryovolcanism, no resurfacing flows, just old ice, old rock, and old silence. There's something quietly moving about this. In a universe where stars burn and explode, where galaxies collide and black holes consume, there is also this. A small, untouched body holding the memory of calm. A relic from the beginning, surviving not by strength, but by isolation, by being forgotten, or perhaps by being too far to disturb. It reminds us that not all knowledge comes from action. Some comes from stillness, from waiting, from simply not being moved. And so Ammonite orbits, slow and steady, carrying with it the first ingredients of the solar system. Not changed, not mixed, not baked or broken, just preserved, like an unopened letter, like a whisper in ice. In time, perhaps, we will send something there, a probe, a spectrometer, an eye that sees beyond reflected light. Perhaps we will touch its surface, taste its ice, read its chemistry in full. But until then, it waits, quietly, patiently, not decaying, not fading, just being. And that, in itself, is enough to make it precious. When light finally reaches Ammonite, it arrives as a traveller tired from a long journey. It has crossed over 300 astronomical units, more than 40 billion kilometres, from the sun to brush against a surface it will barely warm. This light, stretched thin across the dark, doesn't blaze or dazzle. It whispers, it touches gently, and what it reflects, what it gives back to our waiting telescopes, becomes one of the few clues we have to understand what this distant world might be made of. Astronomers call this quality albedo, a measure of how much sunlight an object reflects. A body with high albedo, like fresh snow or an icy moon, bounces light back brightly. A body with a low albedo, like charcoal or ancient dust, absorbs most of it, returning only a dim trace. For a place like Ammonite, albedo is not just brightness, it's a language. One written in photons, one translated by shadows. From here on Earth, or even from the sensitive eyes of telescopes perched atop Hawaiian volcanoes, or orbiting far above our atmosphere, Ammonite is a pixel, sometimes not even that. It is a flicker of movement against the backdrop of stars. It's not what we see in these tiny glimmers, but how they change that tells us something deeper. By watching how Ammonite reflects sunlight, how its brightness shifts ever so slightly over time, scientists can begin to sketch the nature of its surface, its roughness, its colour, its age. Albedo is a surprisingly intimate thing. Imagine walking through moonlight on an icy field. Some parts sparkle, others lie dull and grey. The difference isn't always temperature, it's texture, it's composition, it's the angle at which the frost caught the light. That's what we're doing when we study Ammonite's reflectivity. We're walking its surface with photons, listening for glimmers, reading its landscape in gradients of light and dark. What we've found so far suggests a surface coated in ancient frost. Not the crystalline white of fresh snow, but the darker reddened ice that forms when organics have been bombarded by cosmic rays over eons. Time discolours ice. It weathers it, not by wind or water, but by silence. That silence becomes shadow, and in those shadows, we begin to understand age. The temperature on Ammonite is unimaginably cold, close to 30 or 40 Kelvin. That's about minus 230 degrees Celsius, or minus 380 degrees Fahrenheit, near absolute zero. At such temperatures, even nitrogen, so common and slippery in Earth's atmosphere, becomes a brittle solid. Water ice here is hard as stone. The surface doesn't melt, doesn't flow, doesn't crack from expansion. It simply remains. It's tempting to think of such a place as dead. Nothing moves, nothing grows. But in that stillness is a kind of clarity. The absence of change becomes a record of permanence. In a world where so much shifts and erodes and fades, Ammonite is a place where even the faintest impression might last forever. The darkness of its surface tells us about its past. Low albedo suggests old ice, coated in tholins, complex organic molecules that form when simple compounds like methane and nitrogen are irradiated over time. These tholins are what give many outer solar system bodies their reddish hue, though on Ammonite we can't yet see colour directly. We only suspect it, reading it from faint flat spectra, patterns of light absorption that act like a barcode for chemistry. And in that barcode is a kind of music. It's soft, delicate. The science here doesn't arrive in sweeping revelations, but in hushed confirmations. A slightly redder tilt in the reflected light, a subtle curve in the thermal emission, a brightness that waxes and wanes as Ammonite slowly spins, revealing textures, perhaps a crater here, a slope there. Every rotation is a chance to learn a little more. Every faint dip in light tells us something has turned. A shadow passed, a darker patch faced the sun. These variations, subtle as breath, are the fingerprints of geography. They might tell us about pits, ridges, or patches of ice where light scatters differently. We don't yet know the shapes, but we can begin to feel them. This is astronomy at its most poetic, not about colours we see with our eyes, but about light we interpret with patience. It's the study of frost without touching it, of darkness without dread. We listen to a silent world by reading the way light curls off its skin. To the human body, Ammonite's surface would be unbearable. The cold would seize every cell. There's no air to breathe, no pressure to hold a shape. But to the imagination, to the quiet parts of the mind that wander while falling asleep, it's strangely inviting. A place where even light slows down, where time is not marked by hours or days, but by degrees of glow. And if you could stand there, if your feet could press into the dark frost, you would see no sunrise. The sun would be a pale star, no brighter than a distant beacon. Your dear shadow, if you had one, would stretch faint and grey across the surface, dissolving into the blackness beyond. You wouldn't hear anything, not the wind, not your breath, not even your heartbeat, unless it echoed inside your suit. But you would feel something else, a kind of gravity of quiet, a stillness so complete that it feels sacred. And in that stillness, you might begin to understand why this little world matters, because it doesn't speak in noise or colour, it speaks in tone, in the softness of its light, in the dignity of its endurance, and in the way it waits, with frozen patience to be understood. To stand on Ammonite would not feel like standing at all. There is no true up or down, no firm sensation of weight pulling you into the ground. Instead, there is microgravity, a lightness so complete that it borders on dream. You could take a step and find yourself drifting, not walking. A jump would send you aloft for minutes. There is gravity here, yes, but it is the barest whisper of a force, gentle, persistent, but never urgent. Ammonite is small, and its gravity reflects that. With an estimated diameter of just a few hundred kilometres, its mass is far too low to create the kind of pull we're used to on Earth. A feather dropped from shoulder height wouldn't fall. It would drift, gliding lazily to the surface over the span of a slow breath. And you, if you weighed 70 kilograms on Earth, would feel closer to the weight of a walnut here. Not because you've changed, but because the world beneath you is too gentle to demand your full presence. This soft gravity gives Ammonite its personality. It shapes how its surface behaves, or rather how it doesn't behave. There are no landslides, no quakes, no rapid shifts. If a rock tumbles, it may take hours to come to rest. A meteor impact doesn't create a ripple of destruction. It leaves a bloom of slow-motion debris, floating outward like a shattered thought before settling in silence. Every movement is drawn out, almost theatrical in its stillness. Ammonite also spins, slowly, almost reluctantly. A full rotation might take days, possibly weeks. Its day could last longer than a month. We don't yet know the exact number, but the slowness is inferred by the gradual changes in its reflected light, the quiet rhythm of its turning face. There's no rush, no need to chase a sunrise. The sky above never changes quickly. The stars hang steady, and the cold remains constant. On Earth, a spinning object that's small might eventually wobble or tumble chaotically. But Ammonite is distant, undisturbed. Its rotation, if it ever was irregular, has long since settled into a slow, reliable spin, a lullaby pace, dictated by the inertia of billions of years. And inside that spin, within that tiny world of rock and ice, gravity presses inward in all directions, just enough to hold it together, but not enough to smooth it out. It is likely irregular in shape, more potato than sphere, its contours determined by ancient impacts and frozen time. Still, at its centre, there is pressure. Faint, yes, but constant. The kind of pressure that keeps things quietly intact. It's a different kind of intimacy, to think about gravity not as force, but as mood. On Earth, gravity is loud. It defines our every moment, from the arch of our feet to the pace of our breath. But on Ammonite, gravity is a murmur, a nudge. It lets you forget it's there until you try to move. There's something peaceful about that. To be on a world where you do not fall, where movement is negotiation, not inevitability, where time is marked by the slow roll of light, not the ticking of clocks. To be there would be to feel adrift, not just in space, but in expectation. No wind to orient you, no weight to anchor you, just the low hum of orbit and the soft pull toward a quiet centre. Even within its own body, that calm continues. Unlike Earth or Jupiter's icy moons, Ammonite likely has no layered interior, no molten core or slushy ocean beneath a crust. Its heat escaped long ago, and without enough mass to retain it, the internal world froze solid. No convection, no tides, just stillness layered on stillness, like a book bound in ice and sealed shut forever. If we could place a seismograph on its surface, it would listen to centuries of silence. Occasionally, perhaps, a tremor from a distant impact, a brief hello from a rock that wandered too close. But mostly it would record nothing, and that nothingness would be the data, a confirmation of the world's deep and enduring sleep. And yet, despite all this stillness, Ammonite is not meaningless. Quite the opposite. Its calm gives it value. In its inertia lies the map of everything that came before. Its gravity may be weak, but its memory is strong. The paths it traces, the ice it holds, the spin it keeps, all are records. It is a world that has not been stirred, and so it remembers what others have forgotten. In microgravity, time stretches. A second feels longer. A moment becomes a mood. And perhaps this is why thinking of Ammonite soothes us, because it invites us to enter that mood, to feel what it might be like to drift without falling, to stand without weight, to exist without urgency. It's a strange kind of empathy, to feel connected to a piece of rock and ice you've never seen, that will never know you exist. But that's the magic of astronomy. It allows us to build relationships with the inanimate, to find kinship with distant objects simply because they too are moving through time. And so we think of Ammonite not as empty but as quiet, not as cold but as constant. A little world spinning softly, with just enough gravity to hold its shape, just enough mass to carry its past, and just enough presence to stir something in us when we think of it. A calm within the calm, a stillness that invites stillness. To find something as small, cold and distant as Ammonite, you need more than just curiosity. You need patience measured in years. You need instruments that see not only what is bright, but what is barely there. And most of all, you need to believe that somewhere in the quiet spaces of the sky, there is motion hiding in stillness. Enter the Hypersuprime Cam, a camera so sensitive and so wide-eyed that it can photograph tens of millions of galaxies in a single exposure. Mounted on the Subaru telescope atop Mauna Kea in Hawaii, this incredible piece of technology was built not to chase comets or record eclipses, but to gently observe the deep and far. Its lens doesn't blink, it watches. It gathers light pixel by pixel, photon by photon, until even the faintest objects whisper back. Unlike a human eye, the Hypersuprime Cam doesn't search in real time. It doesn't follow the arc of a star or scan across the heavens like a curious glance. Instead, it stares for hours. Then it steps aside and stares again, and then again. Over days, weeks, months, images pile up like pages in a diary, each exposure a still frame of a sky that seems frozen. But of course it isn't. That's the quiet magic. In those still frames, most stars do not move. They anchor the celestial background, constant, unwavering. But hidden among them, if you know how to look, are objects that do move, slowly, delicately. You might not see it at first. A speck here, then a speck there. A dot that wasn't in the last frame, or one that seems to drift just slightly when everything else holds still. Astronomers use a technique called blinking to spot this movement. It's surprisingly simple, but incredibly powerful. Lay two images on top of each other, taken days or weeks apart, and flip between them. If done right, the stars will appear fixed. But a moving object, a comet, an asteroid, a sednoid like Ammonite, will jump. Just slightly, just enough. A flicker between frames, like a star that has changed its mind. To see this, to notice it, takes not only powerful tools but a way of seeing, a habit of watching. A willingness to look again and again at the same part of the sky, not expecting fireworks, but hoping for whispers. The Hypersupreme Cam is the perfect partner for this kind of science. It is not flashy. It is not hurried. It is, in a way, meditative. It simply observes. With a staggering 900 million pixels and a field of view that captures an area 7 times the size of the full moon, it offers a window not just into space, but into time. Because the objects it sees are not only distant, they are late. The light they send took hours to arrive, and what it records is not presence, but history. Finding Ammonite was not like catching a meteor or spotting a planet through binoculars. It was more like realising that a speck in the background of a family photo has been moving across the entire album, that something was there all along, quiet, distant, unnoticed, until someone, somewhere, took the time to blink between frames. The idea that something so small and far away could be found this way is humbling. It reminds us that discovery doesn't always require leaps. Sometimes it requires sitting still, holding a gaze, comparing what has changed with what has stayed the same. The story of Ammonite's discovery began in frames taken for other reasons. The sky surveys that collect this data are vast, and their goals are broad. Map dark matter, study distant galaxies, chart supernovae. But within those archives lie treasures waiting to be noticed. It took a team of researchers reviewing frame after frame to spot that faint, slow movement that would become Ammonite. And when they did, when the dots aligned, when the orbit began to take shape, it wasn't just a triumph of detection. It was a quiet celebration of endurance, of believing that something could be there, even when everything around it said stillness. What's striking about the Hypersupreme Cam and others like it is not just their power, but their purpose. They are built to listen to the sky in a way that mimics the patience of nature itself. Their sensors wait through cold nights. Their lenses open to silence. Their data doesn't shout, it hums. And from that hum, slowly, carefully we learn. And so we return to that first flicker. Those first 2 frames blinking back and forth. It's such a small thing. A pixel jumping slightly. But that jump means everything. It means this object is not a star. It means it is nearby, at least in cosmic terms. It means it belongs to our solar system. And once you know that, you can begin to trace its path, to estimate its distance, to infer its size and shape and story. It's like finding a single footprint on a frozen plain. It may be faint, but it changes the entire landscape. It means someone, or something, has walked there, and that traces us enough to begin a journey of understanding. So when we think of discovery, of what it means to find a new world, we might picture rockets or heroic explorers. But sometimes discovery is quieter. Sometimes it's a camera that doesn't blink, a scientist flipping between frames, a speck of light that dances just slightly out of sync, and in that gentle motion, against a canvas of still stars, we begin to see the outline of a new world. In many corners of science, speed is the measure of success. We marvel at split-second collisions in particle accelerators. We celebrate discoveries made in the blink of an algorithmic eye. We build rovers and rockets and launch them faster than sound, chasing knowledge at the edge of flame. But the discovery of Ammonite reminds us that there is another kind of science, a quieter one, slower by design, patient by necessity, and no less profound for its pace. To trace the faint arc of a distant body beyond Neptune requires a different rhythm, one that mirrors the object itself. Ammonite moves slowly. Its orbit takes thousands of years to complete a single loop around. The Sun. Nothing about it is urgent. It is a body shaped by billions of years, altered only by soft whispers of gravity and frozen time. And to notice something that moves this slowly, scientists must also slow down. Enter the Fossil Project, short for Formation of the Outer Solar System, an Icy Legacy. Unlike experiments that deliver data in moments, the Fossil Project plays the long game. It's an astronomical effort rooted in slow accumulation, gathering light over months and years, cross-referencing observations from previous surveys, and assembling patterns from nearly imperceptible differences. Its purpose is as poetic as its acronym. These astronomers are looking not for noise, but for residue, for fossils, not of bone or shell, but of orbit and reflection. They're searching for pieces of the solar system that were not swept up into planets or crushed into moons, but left behind, waiting, preserved. And in this mission, the strength lies not in speed, but in persistence. Observatories must return to the same patch of sky over and over. Data must be calibrated with care. Telescopes are scheduled around the lunar cycle, the weather, and the collective availability of instruments across multiple countries. No single person holds the whole picture. It is stitched together, bit by bit, night by night, across languages and time zones and hemispheres. Ammonite's discovery, though a marvel of advanced optics and data analysis, was also an act of old-fashioned patience. It was not spotted in real time or flagged by a sudden burst of brightness. It was sifted from the background, a speck that moved in just the right way, compared to the quiet backdrop of stars. The kind of find that depends less on dazzling insight and more on disciplined, careful watching. And yet, within that slowness is a kind of human brilliance. It takes humility to dedicate years of your career to a discovery that may never arrive. To monitor millions of stars and galaxies, knowing that the one object you're looking for might be 1 pixel wide and might appear only once. It takes trust in the process, in the data, in your team. It takes believing that something important is hiding in the blank spaces, something that won't reveal itself quickly or loudly, but only to those willing to wait. And this science of slowness is not limited to one institution. It is inherently international. The Fossil Project and related efforts draw together researchers from Japan, Taiwan, Korea, China, and Canada, each contributing different strengths, instruments, and perspectives. Some observe, others model. Still others process data, comb through archives, or develop algorithms to flag anomalies. There is something quietly moving about this global collaboration. Scientists in different countries, separated by time zones and oceans, each staying up late to stare into the same darkness. They may never meet in person. Their languages may differ, but they are united by a single question. What else is out there? What have we missed? What whispers are hiding in the noise? These partnerships are not marked by headlines or dramatic moments. They unfold slowly, across email chains, shared spreadsheets, midnight observations in cold observatories, quiet meetings where someone says, "I think we should look again." And from that sustained, gentle persistence comes something astonishing. Ammonite's orbit was confirmed not with a bang, but with a narrowing of doubt. Each new data point didn't explode into revelation. It trimmed uncertainty. The object's position became clearer. Its path through the solar system grew more defined, and gradually a world emerged. Not invented, not predicted, but noticed. And this is perhaps the most important truth. Science is not always about breakthroughs. Sometimes it's about recognition. Seeing what has been there all along and realizing what it means. Accepting that the sky has always held its secrets. Not because it wants to keep them, but because it reveals them only to those who look with care. There's a kind of grace in this. A beauty in a method that asks you to slow down, be still, and trust that what matters will come in its own time. It mirrors the very object we're speaking of. Ammonite doesn't rush. It doesn't announce itself with flares or flukes. It moves through the sky like a sigh, and the science that found it had to match that rhythm, methodical, slow, attentive. So while much of the world accelerates, while data gets faster, expectations rise, and answers are demanded instantly. This kind of astronomy offers something different, a reminder that some truths unfold gently, that the universe doesn't operate on our schedule, that sometimes the most extraordinary discoveries are made not by racing forward, but by stepping quietly into the stillness and listening. And when we do that, when we slow ourselves to match the speed of the stars, we find that even the most distant, quiet objects eventually speak, not in shouts, but in motion. Not in certainty, but in pattern. Not in brilliance, but in time. There's a kind of quiet heroism that happens in the cold. Not the dramatic kind that makes headlines, but the kind that slips quietly into the background of discovery. It happens beneath domes that open like petals in the dark, on mountaintops where frost clings to railings and computers hum beside cups of coffee, going slowly cold. It's the kind of heroism that stares at the same patch of stars night after night, not for glory, not for speed, but for clarity. Ammonite was found at this edge of light, where human curiosity and the ancient silence of space overlap. And it wasn't found by a single pair of eyes, or a single team in a single building. It was found by a mosaic of people. Astronomers, engineers, programmers, students, each one contributing a small piece to a very distant picture. Some of them worked on the mountaintops, adjusting the hypersupreme cam and calibrating exposures. Others worked from offices or labs in cities far from any observatory, poring over datasets, refining orbital models, building simulations that ran through the night. Still others coordinated time across telescopes, handled logistical hurdles, or simply sat with the numbers long enough to see a pattern forming in the fog. The beauty of science like this is not just in the result, it's in the gathering. People from Japan, Korea, Taiwan, Canada, China, different languages, different homes, different nights and days, but united by the idea that something out there was waiting to be found. Not something explosive or urgent, but something gentle, something old, something that would reveal itself only if approached with patience. And so they waited together. They cross-checked data. They sifted through pixel after pixel. They asked one another for second opinions, questioned assumptions, suggested new search parameters. No one was trying to claim Ammonite. They were simply trying to understand it. And that shared goal, that gentle reaching toward clarity, is what made the discovery possible. You might imagine one of those cold nights, high above sea level, the air thin and silent, the observatory dome opening with a mechanical sigh. Inside, a small team of researchers checks the telescope's status, aligns the camera, monitors the night sky through screens rather than eyepieces. There is no drama, no flash of light, only the slow accumulation of exposure after exposure, the kind of repetition that seems dull, until, one day, a dot shifts, a speck appears where it hadn't before, or moves where it shouldn't have, and someone says, "Wait, look at this." Even then, even in that moment of potential discovery, there is no burst of celebration. There's caution first, rechecking, comparing. Does the orbit make sense? Could it be noise, a glitch, a satellite? So the team reaches out, shares the data. Another observatory confirms the sighting. A third helps refine the orbit. The signal is real. The motion is consistent. What they found isn't just a speck, it's a world. That process, the cross-checking, the slow unveiling of confidence, is a kind of music. Not a solo performance, but a quiet symphony, played across continents, each note a confirmation, a contribution, a kindness. We often think of astronomy as a solitary pursuit, a lone figure looking through a telescope, dreaming of distant stars. And that image still holds a certain poetry. But the truth, especially today, is more collective. It's about building instruments no one person could design alone. About processing terabytes of data through tools created by teams. About asking questions that stretch beyond a single language, a single sky. This is why Ammonite's discovery is more than just a new sednoid. It's a reminder of what happens when people trust each other enough to look together. It's what makes this particular corner of science feel not just impressive, but profoundly human. Because this wasn't a race. No one rushed to publish. No one tried to outshine. It was a discovery that unfolded like a conversation. Gentle, slow, full of listening. There's something deeply comforting about that. In a world so often pulled towards speed and spectacle, this was a reminder that meaning can come quietly. That insight can grow not from noise, but from stillness. That science, at its best, is not about having the right answer before anyone else, but about being willing to ask the right question, together. And so, beneath the stars, across oceans and time zones, a community formed around a dim and distant light. They didn't make Ammonite. They didn't name it into being. They simply noticed it. And in that noticing, they wove their efforts into its story. Now, every time we speak of Ammonite, every time we trace its orbit, model its path, imagine its cold and quiet surface, we're also speaking of those who found it. The scientists who waited. The technicians who built the cameras. The programmers who wrote the code. The analysts who trusted the data. The late-night coffee drinkers. The careful skeptics. The gentle confirmers. It's easy to forget that behind every data point is a person. But not here. Not with this. Ammonite moves slowly, but it brought people together swiftly, quietly, across borders, through screens, in late-night logs and shared starlight. And in doing so, it reminded us that even at the farthest edge of the solar system, even in the silence beyond planets, there is still room for us to see, to wonder, to work together in the light of something greater than ourselves. Far beyond the warmth of our sun, past the outer edges of Neptune's orbit and even the lonely path of Pluto, Ammonite continues its slow, frozen journey. It doesn't race, it doesn't seek, it simply orbits, patient, distant, and constant. Like a lantern floating on still water, Ammonite glides along a path etched billions of years ago, unchanged, unnoticed for most of that time. And now that we've found it, what it offers is not just a set of orbital parameters or icy chemistry, but something gentler, a message, a quiet voice from the edge of the beginning. We often think of history as something written in stone or passed down in books, but the universe has its own libraries, and sometimes they come in the form of objects so old, so untouched. They carry the past like a fossil sealed in crystal. Ammonite is one of those rare libraries. Its orbit, its composition, its placement in the vast shell of the solar system, none of it is accidental. Every curve and element is a preserved whisper from the dawn of our cosmic neighbourhood. Back when the sun was a newborn star, still wrapped in the remnants of the cloud that birthed it, the solar system was not yet a calm and orderly place. There were no neatly spaced planets, no icy comets on familiar paths. Everything swirled in a disk of dust and gas, colliding, sticking, breaking apart. In that chaotic nursery, Bodies like Ammonite formed not close to the warmth of the sun, but far out, so far that even sunlight was dimmer than moonlight. And yet, they stayed. They found places to circle. They survived the early chaos not by strength or size, but by distance, by silence. When we study Ammonite, we're not just looking outward, we're looking backward. Its very presence reshapes how we understand the size and shape of our solar system. Before sednoids were discovered, most scientists assumed the solar system ended, more or less, around the orbit of Neptune or Pluto. But Ammonite's long, stretched-out path tells us otherwise. It suggests that the sun's influence, the reach of its gravity, the stretch of its early disk went farther, much farther. Perhaps at one time there were many more bodies like Ammonite. Perhaps the early solar system extended like a vast web, rich with icy fragments and half-formed worlds that never became planets. Some may have been pulled away by passing stars. Others may have fallen inward, burned up or collided. But a few remained, quietly orbiting at the edge of sunlight, waiting to be noticed. And Ammonite is one of them, a survivor, a capsule from the beginning. Not dramatic, not spectacular, but enduring. Its orbit is not just long, it is peculiar, not aligned with the others, tilted, eccentric, different. And in that difference we're reminded that not all stories follow the same arc. Some are linear, some loop, some drift. Ammonite's orbit, stable yet unusual, is a kind of footnote to the great planetary motions, one that says, there is more to this system than what you see. It raises questions we can't yet answer. Was there another planet once, a giant that sculpted Ammonite's path before vanishing? Did a passing star disturb the outer solar system and leave this frozen trace behind? Did these distant bodies once dance in resonance, only to drift apart like memories after a dream? We don't know, but we can listen, we can watch. And perhaps that's the greatest gift Ammonite offers us. Not certainty, but presence. A reminder that not everything has to be understood immediately, that some truths come slowly, over orbits longer than lifetimes, that the universe doesn't rush, and neither must we. It's comforting in a way, to know that even when we move too fast, when our days blur with activity, and our nights feel too short, there are still places where time stretches wide, where nothing is urgent, where a world can take 10,000 years to round the sun and still be right on time. Like a message in a bottle, drifting on frozen tides, Ammonite tells us that our cosmic story is broader than we imagined, that the boundaries we thought were there may not be, that even in the vast cold, meaning can remain, silent but present. And maybe, in hearing that message, really hearing it, we begin to remember something quiet within ourselves, something that doesn't measure life in achievements or speed, but in stillness, in waiting, in orbits of reflection. Because Ammonite isn't just a discovery, it's an invitation to expand our maps, to question our definitions, to slow down, to look again. And as it continues its patient path, far beyond the planets and noise, it becomes not only a fossil of the solar system, but a kind of mirror, a way to see ourselves in the quiet, and to wonder what stories we too might carry unnoticed, until someone, somewhere, pauses long enough to truly look. Somewhere in the distant dark, far beyond where our spacecraft have flown, and long past the warmth of any planet, Ammonite is still orbiting. It doesn't know we've found it. It doesn't care. It's not waiting for us. It's simply continuing as it has for billions of years, along a path shaped by gravity, carved by time and undisturbed by anything else. And maybe that's the most comforting thing of all. We live in a world of speed, of clocks that tick and devices that blink, of messages that must be answered now, of tasks measured in urgency, not meaning. We race through our days, we measure our lives in deadlines and dates, and yet, just outside the planetary boundary, beyond the reach of the familiar, there is a small, frozen world that moves so slowly it seems to pause, so quietly that we almost missed it, so far away that its story could only be heard by those willing to truly listen. Ammonite is still there. It always was. His orbit is long and lopsided but stable. Its body is small but whole. Its surface is silent but storied. It hasn't changed much in the last few billion years. It might not change in the next few billion either. It doesn't need to. Its value is not in transformation, but in endurance, in how it stays and spins and remembers. As you settle in tonight, as your thoughts begin to drift and your body releases the weight of the day, remember that even in the great cold expanse of space there are places of peace. Ammonite is one of them, a quiet world floating in the slow rhythm of an ancient orbit, whispering nothing but its presence. You don't have to race to keep up with it. You don't have to understand all the physics or grasp every detail of its past. It's enough to know that it's there, that it exists, that it carries the memory of the solar system's earliest days in every grain of ice and every curve of motion, that it's still moving, still circling, still silent. Our world is fast. It turns quickly, and so do our lives. We often forget that there are other ways of being, but Ammonite reminds us. It teaches us, not through loud lessons, but through example, through patience, through stillness, through the kind of presence that does not demand attention but rewards it. There's something deeply human about our ability to notice something so faint, so distant, so small. It says something about our curiosity, yes, but also about our longing. We want to know what came before us. We want to connect with the past. And in that connection, we sometimes find comfort. We sometimes find ourselves. Ammonite is not a planet. It's not even especially large. But its orbit, its materials, its improbable survival, all of it speaks. Not in language, not in symbols, but in gravity and ice, in distance and quiet, in the long, patient arc of time. And so, as you close your eyes, know this. You live in a solar system where such things exist, where not everything is loud, where not every discovery shouts. You live on a planet that listens to stars, and sometimes the stars whisper back, through dots of light, through shifts in motion, through the quiet confirmation that we are part of something older, something wider, something that keeps unfolding, whether we watch it or not. Let yourself rest in that. Let the rushing thoughts of the day slow, like Ammonites spin. Let the pull of gravity feel gentle, not burdensome. Let yourself drift, not fall. Let yourself orbit the centre of your own quiet for a while. The universe will not stop. It doesn't hurry and it doesn't pause. It turns and it holds and it waits, just like Ammonite, just like the scientists who found it, just like the quiet wonder in you. You don't have to know everything to feel the wonder of it. You don't have to grasp the math to feel the motion. You are part of this, simply by being. You are already here, already orbiting, already listening. And somewhere, at the edge of all things, a small world of ice and rock continues its endless journey through the dark, unbothered, unbroken, unread by most, but no longer unknown. So, sleep well, little fossil voyager. Sleep well, you who noticed it. The solar system still holds secrets, and tonight it held you.